Okay, good deal. Looks like we're recording. So welcome all. Math 219. Welcome perhaps to your fall semester. Good to see everybody. Now, I'm assuming that this is no one's first class at Duke because the linear algebra prereq, I'm assuming y'all are mostly, if not all, sophomores or older. Anyway, welcome to the class. Now, I've already gone through most of this stuff in the recording that I sent to y'all last week, so I'm mostly not going to go through the sort of the organizational stuff anymore. But I do want to remind y'all that this is all very important stuff, so make sure you watch that recording if you haven't already. Make sure you pay careful attention to it. I am going to I have this nagging concern in my mind that when it comes to course grades, I might have forgotten to talk about one specific point. So just in case, I'm going to go into, you'll see I'm in my sections Sakai site here, and I'm going to click on course grades, and specifically the breakdown of the midterm exams. So I think I may have forgotten to specifically note that not only do they add up to 60 per the course requirement, but that they're going to be specifically 20% each. Okay, so I just wanted to get that said. And then I suppose I should also note that the 10%, that's sort of the instructor discretion portion, that's going to break down like this. So 7% for homework and 3% for attendance. So in particular, notice attendance is going to count a very small amount, right? But it is going to count ever so slightly toward course grade. So I will be actually physically checking attendance. I will be calling names until I learn names, of course. And eventually I will learn names, but it usually takes me several weeks to get to that. We won't start checking attendance, though, until the course roster is at least mostly settled. And that'll be the middle of next week, really at the earliest. Okay. All right. So I think everything else I've already covered. Of course, let me say it again. I know I already said this, but everything on all of these pages you should make sure to read. And there's way too much for me to actually talk through. But do make sure to read all that stuff. And in particular, just while we're here, let me go to the course site. And there's this page called Advice and Resources, and I think this is a really good one. There's a lot of discussion on here that I think will be really helpful. So please give that a look. Okay. So before we get into doing some math, are there any questions about organizational anything? Everybody pretty much understand how the class is going to work? Okay, good. All right. Okay, so let's do some math. I like to start off with, sort of a why are we here sort of thing. Why are you taking multivariable calculus? And very likely, the most immediate answer, at least, for some of you, the immediate answer is because my major requires me to take it. Right? Okay, but why do they require you to take it? I think there's some great answers to that question, and I think you should already believe that single variable calculus is important. I hope that's not, something you're still on the fence about. Right? I mean, this is bonkers important. Anything when stuff is changing, right? Perhaps that'll be important, right? That's what derivatives do. Derivatives understand how things change. So, super important there. And integrals, a lot of people mistakenly think that integrals are about computing areas under curves, which you get right down to it, most of the time, actually not that useful. Rarely is area what we're actually interested in. Usually, we're interested in some other quantity that can be computed with similar techniques to the techniques that we use to computing area. So the area thing is kind of a coincidence, right? It's a geometric convenience, but it's not really what we care about. I'm on a tangent there. What I like to call accumulating quantities. So, for example, if you have let's say, the classical example of a rod, one-dimensional rod, where the density is not constant. Maybe it's more dense on this side, less dense on this side. Mass per unit length is higher over here, lower over here. How do you compute the total mass over the total length? And you can't just multiply density times length because, well, the density is not constant. Well, what you can do is you can chop it up into little pieces, and the whole mass is the sum of the pieces of mass. And this is what I call an accumulating quantity. And it turns out there are lots and lots of accumulating quantities out there. And again, y'all have taken single variable calculus classes and you've computed lots of stuff. So again, very important. This is all single variable calculus, of course. Okay, so why do we need multivariable calculus? Why isn't single variable calculus good enough? Well, short answer, because the world's not one-dimensional. Right? We live in a three-dimensional world. At least. Right? That's a nod to the theoretical physics world. So some easy examples, easy pickings here. So suppose you have temperature as a function of position. Now again, highly plausible. Even in this room right here, temperature, I think I could persuade you, it depends on where you are in the room. So over there by the window is probably a little warmer. Right? Somewhere in here, we hope there's an air conditioning vent. I guess it's probably a little cooler by that. So temperature depends on position. Position is described by 3 variables. And so if you want to know, let's suppose that I'm sitting here at this point and I'm going to start moving with that velocity, and I want to know how fast is the temperature going to change as I move with that velocity. Well, it's not a single variable calculus problem. We've got 3 different variables that are changing here. X is changing, Y is changing, Z is changing. How do I deal with the fact that multiple of the input variables for the function I care about are all changing? Well, this is a multivariable calculus question. This is one of the reasons why we study multivariable calculus. And again, ultimately, what it boils down to is it's because the world is 3-dimensional. Right? Not 1-dimensional. Okay. Analogous to the mass of a 1-dimensional distribution of mass, suppose you have a 3-dimensional distribution of mass. So a lump. Right? In fact, this is easier to visualize than a 1-dimensional rod, right? If you think about it, I mean, we live in a 3-dimensional world. It's kind of hard to visualize a 1-dimensional rod. But a 3-dimensional lump of mass, I've got tons of those in my yard. Right? This is a highly relatable question. And very often it's the case that density depends on position. It's not uniformly dense. Right? There's a section that has more iron in the alloy, and maybe there's a section that's mostly dirt. So highly variable. So how do you compute the total mass? And so again, you can't just compute mass as mass per unit volume times the whole volume, because the mass per unit volume is not constant. And so what do you do? Well, so there's a lot to say about this, but ultimately, this is an accumulating quantity, and we are going to do what I like to call chop it up, add it up. In other words, break this up into a bunch of little pieces, look at each individual little piece, and it's going to work out, the details to come, that on any individual little teeny tiny little piece, it's a fairly easy question. It's just density times volume on each little piece. And then we're going to, details to follow, but we're going to figure out how to add that up over the entire 3-dimensional region. And so, again, this is a highly multivariable calculus question. You cannot solve a question like this with mere single variable calculus. So those are some obvious, low-hanging fruit answers to the question of, why do we need multivariable calculus? Well, we live in a 3-dimensional world. Okay. So I claim it's worse than that, though. And so here's an example from, I'm going to say from economics. Appropriate. We're in the economics building, kind of, I suppose. So suppose you have various quantities, and I picked these letters because these are letters that economists use to represent price, quantity, interest, etc. And suppose you have some economic model. And economic models tend to be written as, some great big equation, or quite possibly several great big equations involving a bunch of variables that are involved in the model. So you have this economic model, and, this being a model of things happening in the real world, and the real world things change. Let's suppose that the labor is changing and the capital is changing and the quantity of whatever is changing and interest rates are changing. And maybe you know what these rates are. You can keep track of how those rates are changing. With the understanding that P has to do what the model says it does. Right? This model must be satisfied. That's why it's a model. That's why we write it down in the first place. With that understanding, and the understanding that these other quantities are changing in certain ways, well, how is P going to change? Right? So now this is about changes and derivatives, so it's clearly a calculus problem. But there's a bunch of variables involved. So this is not single variable calculus. This is multivariable calculus. And a lot of people would say that this is that there's 5 variables here. I would point out there's actually 6 variables, right? Because time is a variable as well. Anyway, very often people will call this 5 plus 1 because there's 1 input and 5 outputs that then are kind of in some sense inputs to the model. Anyway, so there's a bunch of variables. So the 2 things I'll say about this is, for one thing, again, yes, we need to understand multivariable calculus. Of course we do. Wow, right? If you want to understand economics, for example. But it's, like I say, worse than my previous examples, because check it out. You can't just limit yourself to 3 dimensions. And this isn't even some sci-fi, abstract, far-out physics, theoretical nonsense example. This is just economics, right? You need more than 3 variables, not because we live in a greater than 3-dimensional world, or we might live in some, high 4-dimension. The 4th dimension sounds really scary when you say it, right? But 6 dimensions is not hard to visualize as being a relevant question to understand when you look at examples like this. How are we doing? Is everybody on board? Okay. All right. Okay. All righty. Now, real quick, just for fun, I'm going to throw you into some of the stuff we'll be doing near the end of the course. It's going to look like this. So we're going to cover a lot of math in this class. Y'all are going to walk out of here having seen a tremendous amount of material. And real quick, I'll point out this is what's called Maxwell's equations. Well, these are technically special cases, the common special cases of Maxwell's equations that describe how electricity and magnetism work, or at least in certain aspects of how E&M work. What does all this mean? Right? What's this thing? What's that thing? It looks like a differential, but it also looks like a vector. That's creepy. What's going on there? Right? So we need to know those, what do these things mean, but we also need to understand the equations. And so like this statement, let's see if I can, this statement here, how can I make sense out of that? What is that really saying? Right? And then furthermore, what does that statement, if I understand what that statement is saying, what does that tell me about electric fields? Is there a way to visualize? Can I connect what this is saying to other aspects of electric fields, and how can I use that? Right? These kind of things are very important and pretty sophisticated questions. And ultimately, multivariable calculus is going to be how we're going to do all that. In some sense, Maxwell's equations are really just statements about what you might call multivariable objects. And there's a ton of stuff to say about this, and I'm going to have to restrain myself, not to talk too much about the physics. It is really, really fascinating stuff, and it's really, really important stuff. Maybe the one thing I'll say is this. If you have not yet had a course in E&M, then you're going to be at a huge advantage when you do take that course, because you're going to already understand the multivariable calculus. You'll really understand what this is saying already. Without even realizing it, you're accidentally going to understand a huge amount of E&M just from understanding the multivariable calculus that's behind what these things are saying. And then you'll get into an E&M class and it'll be unfair with the other students. At least that's how I felt when I took E&M. I was in this situation. I had multivariable calculus before E&M, and I just sweet. Let's see here. Last thing I'll point out, Schrodinger's equation. Y'all may have seen this before at some point in some sense. Why should we care about it? Well, quantum mechanics describes how matter works. What's the fundamental nature of matter, right? But an easy example of why we should care about this is, from chemistry, let's say, is molecular bonds. You want to understand bonds between atoms, require understanding electrons, and electrons obey Schrodinger's equation. So this, in some sense, this is deep down underneath it all, what describes how molecular bonds work in chemistry. So if you're a chemistry major, well, that's, it's worth knowing a little bit. And why does this have to do with multivariable calculus? Well, this thing right here, that is a shorthand notation that represents certain kinds of multivariable derivatives. In other words, that is an object of multivariable calculus. So this is an equation in multivariable calculus. Specifically, this is called a partial differential equation, and we're not going to do, that. We're not going to be solving Schrodinger's equation in this class. But when you take future class, if you take PChem, for example, you'll probably solve the Schrodinger equation of the hydrogen atom, for example, which is kind of the easiest possible case. But you might call it advanced multivariable calculus. Okay. Alrighty. So, altogether, and again, let me remind you, what are we doing here? I'm addressing the question, why is multivariable calculus important? And so my altogether answer is because it's the calculus of the real world. I think that's a fair statement. Again, the real world is three-dimensional. The problems that we solve in the real world involve bunches of variables, likely even more than three. And so if you're doing actual rubber meets the road business in the real world using calculus, you're doing multivariable calculus. Okay, so that's my pitch. Let me pause again for questions. What do you think? Everybody okay? All right. Okay. All righty. Yeah, okay, so moving along, now we're going to jump into the book. Now, of course, there's a lot to do, to work up to the exciting stuff that I just showed you. We're going to have to start at ground zero. By the way, just in case you're curious, this course is highly, I'll say what's the word for it, it's highly trimmed, leaned out. We've removed as much as we can possibly remove to get to the, to get to the big finish of the class, and we do that because there's so much material to cover that we kind of have to keep this course as lean as we can in order to just be able to fit everything in. That said, some of the stuff we're going to do, it won't be immediately clear why we care about them, but we will get there. So bear with me. Okay. Oddly, I am going to start with section 1.6. This is mostly linear algebra, and as is a lot of chapter 1 is linear algebra, and y'all have all had linear algebra. I assume most of you have had 218 -1 or -2, either one. Welcome to you both. Some of you may have had 221 super. As far as we're concerned, those are morally equivalent. But anyway, so I'm going to hit a few things, though, that I think either you might not have seen in a linear algebra class, or that you might have seen, but you might have either not digested as well as would be ideal, or just important enough that they deserve to be hit again anyway. So I'm not going to cover all. Correction. I'm not going to spend class time on all of what's in chapter 1. It is all fair game, right? And again, y'all heard me talk about the content syllabus And, so exactly what's fair game and what's not fair game is documented pretty thoroughly here. So yeah, I am excusing you from that business there and this business here. But pretty much other than that, the rest of Chapter 1, all fair game. But I think you're going to find a lot of it to be review. So anyway, hitting certain highlights. Starting with 1.6 because it's really linear algebra. So I think this is it's good to get this settled and established as soon as possible. So make sure to review it. All the stuff, despite the fact I'm only going to talk about some of it. So the triangle inequality, this is a pretty easy thing to believe. It basically says that this length there is less than the sum of these lengths there, which you might take as interpreting that the shortest distance between 2 points is the straight line distance between those 2 points. I think it's pretty easy to believe. How to actually prove this statement is a linear algebra problem, and this is not a linear algebra class, so I'm not going to spend class time on that. But anyway, make sure you've seen it, and if you're curious, you might entertain yourself with the question of how would you prove this. All right, next, matrix multiplication. I'm very confident that y'all know how to multiply matrices. What I want to double check is that you know all of the ways to multiply matrices. And a lot of students are told in high school math classes that, it's this dot product formula where you take the rows of the left matrix and the columns of the right matrix and you do a bunch of dot products and you compute the product one element at a time. From a point of view of performing arithmetic, hard to beat that one. The thing is, we don't focus a lot on the performance of the arithmetic, right? If you may recall in math classes you've taken before, what we're interested in is how do various objects relate to each other, right? We're interested in connections between mathematical things. And this point of view here, I think, does that in a arguably better way, in a way that really shows up and is useful more than the other. So notice what this says. This statement here says that a matrix vector product is a linear combination. Specifically, it's a linear combination of the columns of the matrix. So a matrix vector product is a linear combination of the columns. That right there is already a connection between ideas, right? Matrix multiplication is a mathematical concept. Columns are a different mathematical object than the matrix itself. Right? They make up the matrix, but they're parts of the matrix in a very specific way. And then furthermore, in what way is this product a linear combination? Well, we use the vector, specifically the coordinates of the vector, as our coefficients. Okay, so I hope you all have seen this before. If it wasn't focused on, perhaps, in your linear algebra class, then you want to make sure that you're good to go with this point of view. Okay, how we doing? Okay. All right, moving along. Linearity. Now, linearity, very important in linear algebra, right? This is where the linear in linear algebra comes from. But there's this weird phenomenon that, of course, there's a lot of material in linear algebra, and y'all spend a lot of time thinking about, row reductions and decompositions and so much stuff in there, right? Orthogonality and so many things to do in a linear algebra class, and very often students get out of there having focused so much on the methods that they forget the very basic, the very fundamental. It's surprising how many students don't really understand what the word linear means. So this is just a quick reminder, just to make sure that everybody's clear on what linearity is. If we have a function, a Euclidean function, so Rn to Rm only, no abstract vector spaces involved in what we're going to do here. Linear means this. It means that if you have some various vectors and scalars, if you do the linear combination before you plug into the function, versus if you do that same linear combination here, you'll notice, after you plug the vectors into the function. Same. Right, so there's different ways that you can think about this. So again, you can think of it as what I just said. People like to streamline that statement by saying that linear functions commute with linear combinations, in the sense that you can do the linear combination before or the function before or after. It doesn't matter which order you do it in. It's not technically a commutativity, but it feels like a commutativity. So that's the term. So anyway, that's just to be clear what linearity is. Of course, it comes in different versions. You can say it as these two statements together, if you prefer. You can say it as a linear combination involving more than two vectors. Doesn't make any difference. These are all equivalent. So basically, when you're proving things, it's nice to only have to deal with two vectors. Right? When you're invoking linearity, it's nice to have the flexibility to involve as many vectors as you want. Yes.
I'm kind of confused about a function t and then how t is kind of multiplied on the bottom. I don't understand.
I'm sorry. Say again, please.
So at the top
Yep.
definition, a function t,
right?
The colon.
Yep.
And then what does that mean when you're going down?
Is it this notation here that you haven't seen before, perhaps?
Probably.
But okay. Let's clarify on that. So this notation with the colon and the arrow is this is a mathematical shorthand, and what it's saying is this is the name of the function. Functions have a domain and a target.
Yeah.
The thing at the beginning of the arrow is the domain of said function, and then the thing at the end of the arrow is the target.
Okay.
So what this is saying is that we've got this function called t. It applies to all of the vectors in Rn. So in other words, any vector in Rn you can plug into this function. And when you've done so, what comes out will always be a vector in this space right here. Yeah. Does that clarify what? Okay, cool. Yeah. So another way you might say it is, you made reference to things happening down here. It's saying that, for example, this is an element of Rn. And it's saying that, but then what comes out is an element of Rm. Yeah. Cool. Anybody else? Okay. All right. So linearity. By the way, the word linear transformation is just a fancy way of saying it's a function that's linear. That's it. So, big word, little concept. A couple of quick examples. Now, this is where I'm choosing these examples because it's possible you might not have seen these specific examples of linearity. And so this is a two birds, one stone. This is I'm showing you examples, but also I'm making sure that you're aware that certain things are linear. So, if you fix some vector A, and if you define a function P as, dot product with that fixed vector A, then this is a linear transformation. So this function is linear. Okay, and a lot of people will streamline this statement by saying dot products are linear. And to be fair, technically what they're saying is the function here is linear, but what is the function? The function is, it's a dot product with a fixed other thing. So dot product in the sense of one of them being fixed and viewing as a function of the other. Dot products are linear. Okay. All right. So likewise, and this is the one that always seems weird, but cross products, thought of as a function, are linear also. And You can check this for yourself. You can just straight up go up here and confirm that that works. And if you haven't done it before, and if you're a little suspicious, perhaps that I'm putting one over on you, check it. It works. Okay. Last one, and I'm a big fan of this last one here. When I taught linear algebra, I used this fact a lot. Very, very useful fact of linear algebra. I don't know how Math 218 does it. So again, I'm using this as an example, both because it's an example and because I want everyone to make sure to know this specific fact. So there is an aspect of determinant that relates to linearity. Now I want to emphasize determinant itself, not linear. Determinant of a sum of two matrices is not usually cannot be assumed to be, I'll say, the sum of the individual determinants. So determinants not linear. Oh yeah, question.
Could you explain the first two examples again?
Okay. What specifically were you confused about?
Like, what's the difference between the first two examples?
The difference between these first two examples? So the difference is that in this first example, the function's defined with a dot product. And in the second example here, the function's defined with a cross product.
Okay.
Yeah, and those are just different operations that, from 218. Yeah. Sure. Okay, so this about determinant. Again, determinant itself, not linear. But you'll notice that this function that I'm defining here, this d, is not determinant. Determinant is a function of several input vectors. Right? There's a bunch of vectors that go in to determinant. There's an entire matrix, you might say, that goes into the determinant function. I'm talking about a different thing here. I'm talking about this function called d. D says we're going to take the determinant of a matrix formed where the first n minus 1 of those rows have all been fixed. This is, the D itself includes both the fact that I'm eventually going to take a determinant and the first n minus 1 of my rows. And this function applied to a single vector x that will take that last position there as my last row. This function d is linear. So some people will say, and this there's a lot of mathematical slang where people say, things in the way that's a little ambiguous, but nevertheless kind of gets as efficiently as possible at what's trying to be said. People will say that determinant is linear in its last row. And again, there's a lot of ambiguity in what that means, but you can see why people would say it that way. So, so this function d is linear. Side note, doesn't have to be the last row. I chose the last row just for kind of, coloring convenience, right? But you can use any row you want. Still works. So, determinant is linear in its last row. Determinant is linear in its next to last row. Determinant is linear in its first row. Determinant is linear in all of its rows. And by the way, determinant is also linear in all of its columns. You can think through for yourself what that statement means. So because determinant is, now again, itself fully not linear, right? But individually all of its rows and individually in all of its columns, it is linear in each of those parts. We say determinant is multilinear. So I don't know if y'all heard that term before. Just quick show of hands. How many people have heard the term multilinear? No. Okay. All right. So determinant is multilinear. That's just a fancy way of saying this, that it's determinant in individually each of its rows and columns. Okay. All right. Okay. So, another really important fact here. This equivalence right here. These two statements are the same. So on the one hand, if you have a Euclidean linear transformation, but by the way, Euclidean is just the way I communicate that both the domain and the target are Euclidean spaces. So if you have a Euclidean linear transformation, then there is a matrix. Specifically, there is a matrix. Oh, shouldn't use blue there. There is a matrix A that computes that linear transformation by multiplication. And this is if and only if it goes both ways. So not only is every function of this form a linear transformation, but furthermore, if you have any linear transformation, then you can write it in this form. So now again, I hope this is something y'all have seen before. Quick show of hands, how many people have seen this fact before and remember it? Okay, all right. Well, so I'm glad we're reviewing it here. Yeah, question. Oh, thank you. I always forget which math symbols y'all have seen before. So this is a little shorthand. It means there exists. Yeah, in fact, let me write that down here. So this means there is or there exists. Okay. And by the way, there's going to be other mathematical shorthands that I'll be using here and there throughout the class. And please don't hesitate to ask. No problem. I'm happy to clarify. They're standard, and so I forget that y'all haven't seen them before. Okay. All right, so let's talk about this statement. Why is this true? By the way, it's a pretty surprising statement if you really think about it. Linear transformation is not a constructive definition, right? It's a property that a function has. But when I say t is a linear transformation, I'm not giving you an explicit formula for how to compute t. So how can I, if I don't even know how to compute t, how can I know that there's a matrix that computes it? So it seems a little weird that I'd be able to draw this conclusion. And the argument is a beautiful argument, ultimately very simple argument. Let's first observe that if you want to prove that direction, that's plug and chug. This is, you get to assume that you are dealing with a matrix formula here, and you just have to check that it has the property of being a linear transformation, and you can just look at the previous page and just confirm that it has those properties. So that part's straightforward. But going the other direction, all I'm going to assume here now is that my function is called t, and that it has this property of being a linear transformation, and I'm going to show that a matrix exists. Not only am I going to show that this matrix exists, I'm going to find an explicit formula for this matrix. Here's how it works. Super clever. First, let's observe that if I have a vector x, that x is a linear combination of the standard basis vectors. I'm going to interject a quick reminder here because I think a lot of y'all, just based on experience from teaching this class a few times before, might have forgotten what these standard basis vectors are. Let me write this down. So, EI is a vector that is mostly zeros. But there is a single one among these mostly zeros, and that one is in the ith position. Does that look familiar? In some classes, these are referred to as IJK. But the problem with the IJK convention is that it really works best in 2 or 3 dimensions. If you're doing math in more than 26 dimensions, then you've already run out of letters. Right? And plus it's just, it's not an efficient use of letters. So anyway, I like this E subscript convention to describe the standard basis vectors. Okay, so any vector is going to be a linear combination of the standard basis vectors. In some sense, that's the definition of coordinates, where coordinates come from. That said, now let me apply the linearity. Keep in mind, right? I'm assuming that I have a linear transformation, so I get to use linearity. And linearity says linear combination on the inside, linear combination on the outside. So all I'm doing is what I am explicitly, by assumption, allowed to do. And now I make the clever choice. Really clever choice. Here's the move. The move is you take these things, the images of the standard basis vectors, make them the columns of a matrix. Now, free country. Right? I'm allowed to do whatever I want. I've got these things. I've got this function t. I can plug in and compute what the images of standard basis vectors are, and I now choose to take those results and make them columns of a matrix because, again, I'm allowed to and I want to. And now why I have done this and what does this show and in what sense is this helpful is now on me to demonstrate, right? But I'm allowed to do this, and I'm going to choose to do it. I saw a hand somewhere. No? Everybody good so far? Okay. So, all right. So, now where were we? Let's see here. We were... at that point right there. And keep in mind that the images of the standard basis vectors are these A1 through A, or these, AI vectors. Okay, let's plug that in. And lo and behold, what I have now is a linear combination of the columns of a matrix, where I am using certain numbers as my coefficients. Well, this is the definition then of this matrix times this vector. Going back to that previous point of view that I gave y'all on how to think about matrix multiplication. Matrix multiplication is a linear combination of the columns and all that. So, sure enough. Okay, so we win. Let me just remind you what we've just won. I claimed that if we have a linear transformation, if you just simply allow me to use this property of linearity, I claimed that I could find a matrix that computes T of x as AX. And check it out, I did it. Here's the matrix called A, and sure enough, T of x is AX. So, win. All right. Everybody good? So again, I just want to make sure everybody's good. I mean, this particular proof I think is really important. It's important to understand that linear transformations relate strongly to matrices, and furthermore, it's important to make sure you understand all the kinds of steps that we took here, viewing vectors as linear combinations of the standard basis vectors, using linearities, etc. Okay, so we're going to use this fact in this course substantially. Okay, last thing I want to tell you about 1.6, about linear algebra in some sense, is don't forget that matrix multiplication corresponds to compositions of linear transformations. And this is another really big one. You might even say, by the way, that this is why we multiply matrices the way we do. I don't know if this has occurred to you to think about it in the past, but it's a pretty weird formula, right? How we multiply matrices is strange. Why? Who dreamed up this oddball formula for computing how would I compute a product of matrices? And the reason I like to think of it anyway, the reason why we have that oddball formula is because that's what it has to be, so that multiplying matrices corresponds to composing their corresponding linear transformations. It's just a matrix algebra point of view on this existing unavoidably natural concept of I might want to compose functions. So, a really important fact, often underappreciated, underemphasized. Okay. All right. So that's 1.6. Oh, again, there's a bunch of other stuff in 1.6. Make sure you read that. Make sure you're good. We're going to cover section 1.1 now. We're going to do this ultra fast because, again, it's all stuff you've seen before. And again, I'm just going to hit the highlights. I think I mentioned this in the organizational recording, by the way, which is I really am not going to have time in class to talk about everything that's in the book. That's just not feasible. So I'm going to pick and choose what we spend class time on based on what I think you can most benefit from hearing discussion of. And sometimes it's going to be the hardest ideas, and sometimes it's going to be the most subtle ideas. And it's going to be a combination of, examples and abstract discussions, etc. But the intention of all of that decision making is to maximize, what you can get out of the course. So there will be a lot of, I'm just going to have to skip this part and leave it to you to read because there are other things where we can make more effective use of class time. Okay. All right, so I have only a few quibbles to discuss in 1.1. The book uses bold to indicate that it's talking about a vector, and it looks cool and everything, but it's a little bit of a show-off move by the book being printed and typeset. Because if we're going to be doing math and handwriting, that's pretty hard, right? To bold, you got to sit there, and it just takes a long time to make a bold. It looks weird. So I prefer, even in my non-handwritten stuff, I prefer to use the little vector hat thing. And of course, the little hat means it's that little thing right there, because it's easier for people who are handwriting. So anyway, heads up. Book does it one way, I do it a different way. Another little complaint that I have is the book will represent this with that notation. Now, okay, fine, it's just notation. They can make their choice. But I like to point out that vector can also be thought of as P2, thought of as a vector, minus P1. Thought of as a vector. So this is an alternative way to write that same thing. And what's the difference? I mean, who cares if I write P1, P2, if I write P2 minus P1? Not much difference, I suppose, but the way I look at it, the main difference is the fact that this shows algebra. I can see that there's an algebraic operation. I'm explicitly indicating that there's an algebraic operation in there, and I think algebra is a good thing. Right? I don't want to sweep it under the rug that there's algebra available for us to take advantage of and do algebra with. I want to emphasize that there's algebra happening and that we can do things with. So you'll never see me write this other than to explain that I never write this. And I strong preference for this. Y'all can, of course, do whatever you want. Okay. All right. Okay, so that was section 1.1. Again, make sure to read all the rest of it. There's a lot of other little things in there. Okay, so again, with section 1.2, there's a lot of other things. I'm going to focus on the things I think are most necessary to talk about. You might very likely have not ever seen before this thing called a parameterization. A parameterization is a kind of a function. It's a very specific kind of a function. A parameterization gives position as a function of a single parameter. And very often this single parameter, very often we think of that single parameter as time. So it's tempting to call a parameterization position as a function of time. I mean, again, you can kind of think of it that way, and that's a fine way to think about it, but technically it doesn't have to be time. So just to be more general, I'm going to say position as a function of a single parameter, and yeah, probably time. Okay. So here's an example. Here is a function that gives position as a function of a single parameter. In this case, I'm calling it t, and I want to think of that as being time. So we've got position as a function of time. And here's the explicit formula for how position is a function of time. So the x-coordinates are cosine of t, y-coordinate sine of t. So a couple things you can notice about this. For one thing, you'll notice that x and y have an easy to notice relationship, right? Sine and cosine, we have this known fact that sine squared plus cosine squared is 1, and so x and y have that same relationship, and that means that this thing that I've got, this parameterization, let's do it like this, this parameterization, all the points that come out of this parameterization, they all satisfy this equation, and therefore they are all on that unit circle in the xy plane. So that's the first observation I'm going to make about it. Next observation I'm going to make is you can actually just walk through and see what happens. What does this parameterization do as my parameter, right? Time, t, as my parameter increases. So let's look at, for example, when t is equal to 0, plug in t equals 0, and you get 1, 0, which is right there. And now you can plug, let me denote that is where t is equal to 0. And now what happens if t increases just a little bit, right? Let's make t, 0.1. Something like that. As if t is a little bit bigger, then cosine will be a little smaller, sine will be a little bigger, and, well, you're going to be there. And as t continues to increase, you can just watch it trace out. As t increases, you can watch it move around this unit circle. Yeah, question.
How would this work if we went into more dimensions?
If we went what?
If we went into more dimensions.
Oh yeah, I've got a bunch of examples to come. We're going to see some higher dimensional examples. We're going to see some 3-dimensional examples. I'm not going to do anything in 4 dimensions. Okay. With parameterizations. Okay. Yeah. So yeah, you can just kind of watch it trace out the circle. And again, that's the nice thing. If your input is time, then you're literally drawing the parametric curve. You're describing the motion of the pen as you give position as a function of time as t moves around the curve. So this draws the unit circle. Everybody good there? Oh, I'm sorry. I realize now I'm over time. 11. Yeah, because we end at 11:05, I believe. Right? Okay. So sorry to go over. So we are done through whatever page that is. Looks like that's page 4. We'll pick up there on Wednesday. Y'all have a great Monday. See you later. Oh, and let me stop the recording here.